Good morning, good afternoon, everyone. Welcome to this webinar about QuEra's quantum computing roadmap. My name is Yuval. I'm Chief Marketing Officer of QuEra. I lead QuEra's global sales and marketing activities. And I have the pleasure of having us joined by Alex Keesling, CEO of QuEra. Hey, Alex.
Hi, Yuval. It's great to be here. I'm very excited about the announcements that we have coming up and to see so many people join this webinar.
And we're excited to have you. Alex not only is the CEO of QuEra, but while at Harvard, he co-invented the technological platform that serves as the basis for our product. Just a couple of housekeeping items. This session is recorded and we'll make the recording available later. Also with some surprise email after we're done. There's a Q&A box and I encourage everyone to submit questions. I'm not sure we'll have time to answer questions live, but we'll do our best to get back to you immediately after the webinar and try to address all the questions. Yes, we will share the presentation and the recording. So Alex, the next slide, please. Very good. So here's what we're going to do today. We're going to talk about new capabilities for analog quantum computing, which is the product line that we have right now. We're going to talk about the need for quantum error correction, the key building blocks that get us to quantum error correction. We're going to talk about a new product, the logical qubit simulator, that can help people get ready for the era of logical qubits. And then one more thing, which is probably going to be the highlight of this webinar. But before we do that, let me tell you a little bit about QuEra. So QuEra is based in Boston. Our company is about 4 or 5 years old. We've been spun off initially from MIT and Harvard and to commercialize a lot of the innovation that happened at that time. Today, we employ about 50 people, mostly scientists and engineers from Harvard, MIT, and other top-tier institutions. We believe that the future of quantum is with large-scale error-corrected devices, and we've been working diligently these few years to make it happen, and we'll share the progress and our plans on that. One of the things that makes QuEra unique, and we'll talk a little bit about our history later in the webinar, is that we're able to take innovations from the lab, whether it's QuEra Lab or MIT or Harvard, and basically turn them into working products very, very quickly. This is one reason that for, I think, 15 months now, we have the first and currently the only neutral atom quantum computing that's globally accessible. Dozens of users, dozens of organizations, hundreds of users already use our products, and a lot of their work has been published, and we're hiring. So if you want to join the team, there's going to be a link at the end of the webinar. Many, many exciting positions. Next slide, please. And so I'd like to start by describing new capabilities for analog quantum computing. And Alex, perhaps you can tell us a little bit what analog quantum computing is, how is it different than digital, and then what are the new capabilities that we're bringing to market this year?
Absolutely. Thank you, Yuval. And once again, thank you everyone for joining this webinar. Let me take a moment just to talk about analog and digital. These are two different approaches to quantum computing, both of which are supported by the physical platform that we have been developing at QuEra over the last several years. They both have different strengths in terms of what they can offer to users. Particularly in the analog mode, we have already put out a product that is available to all of you online that allows users to not only program a quantum circuit in a set of instructions for the evolution of the processor, but also define the connectivity of the processor itself. This is what users can do today by selecting where qubits are placed relative to one another and how that defines a connectivity. This allows for a very powerful way to take problems and map them directly into the hardware in a very efficient way. The analog part of this is that the instructions, the quantum algorithms, are written in a way that defines the real-time signals that go into the processor in an analog way, and that effectively implement an algorithm through the evolution of what we call a Hamiltonian. This is in contrast to the digital approach to quantum computing, also supported by the physical platform that we've built, in which all of the algorithms are broken down into sets of individual and 2-qubit gates that then take an abstract representation of an algorithm and break it down into this representation. What this means is that the analog approach is a very useful way to use the resources that we have available right now, reducing the overhead and adding an extra layer of protection against noise. But the digital mode of operation, of course, is something that allows for a much easier way to abstract the computation and to make it universally applicable. Now, our first product, Aquila, works in the analog mode. This is the first and as Yuval mentioned already, the only globally available neutral atom quantum computer to the general public. Aquila has been a great experience for us here at QuEra, thanks to the very positive user engagement that we have seen. It has, over the last year, increased the availability on the cloud from only 10 hours at the beginning to over 100 hours today to support all of our customers worldwide. We have used this to open the doors for new applications to be developed on top of it. And we have seen lots of exciting progress in using it for areas in quantum simulation, quantum optimization, and machine learning, some of which have resulted in publications which we are very happy to support, and to support even more directly by opening up a premium access mode over the last year so that our end users can engage directly with the QuEra team members to work through the process of converting the problems that they have into the right algorithms that run efficiently on hardware. And on top of this, just at the end of last year, Bracket, our partner to make this technology available to users all over the world, created also the Bracket Direct program, in which we participate to allow users to reserve machine time and have exclusive access to the processor over the time that they reserve, and also to have a closer working relationship both with the QuEra team and the Amazon Bracket team. We're very excited to continue to support the customer success stories that have already started coming out of users engaging with Aquila, and we are looking forward to more this year. Now, looking forward to the rest of the year, there's more that we want to make available to customers and that we will make available to customers. We have listened to the feedback to understand what are the tools that will allow users to expand the set of use cases to cover the problems that they care about. And looking forward to some of the things that are coming up this year. For quantum optimizations, we have worked with customers to enable them to solve problems that are represented as a maximum independent set type of problem. Over the rest of the year, we'll enable new capabilities to expand this to be a weighted maximum independent set, QUBO, and other types of combinatorial optimization problems. Similarly, we're going to expand the set of geometries that users can access to give them more freedom and flexibility in the types of problems that they can encode, both for optimization and quantum simulation. We are expanding the toolbox that we have available for customers so that they can now start exploring a wider set of use cases in machine learning, particularly extending the concepts of reservoir computing to the quantum realm. And last but not least, we are very excited to offer customers now, later this year, a way to initialize the state of the processor in other initial states to expand the set of use cases that they can explore in optimization, in simulation, and in machine learning. Now, all of this is what we've been doing on the analog side. Of course, as I mentioned, the physical platform that we have built supports both analog and digital, but so far we have focused on the analog only. But this is something that we think will change very soon. And particularly one of the things that we have been paying a lot of attention to, as Yuval mentioned at the beginning of this presentation, is the need for quantum error correction to make the digital operation more powerful. Yuval, what can you tell us about this need?
And
what have you heard?
Before we go there, I just want to recap some of the interesting things about Aquila and analog mode. So this is a computer with 256 qubits. You can access it right now on Amazon Bracket. Some very exciting papers. There's a BMW optimization paper. Just this week, we released a paper on quantum reservoir computing, so new methods for machine learning that are very promising in this way. And 256 qubits, fully coherent with very flexible control, allows solving some very interesting problems. But to get to universality, to get to, say, any quantum program, to say, oh, I want to be able to one day run Shor's algorithm, you're going to need digital mode, gate-based mode for that. And the problem has been that digital gate-based computers have errors, and the errors limit the length of the calculation that you can make reliably. And therefore, a lot of people have spoken about quantum error correction as the potential solution. So maybe, Alex, you can describe what is the problem and what can be done about it.
Yeah, and you already, I think, set up the problem very well. At this point, the error rates that are introduced by performing the simple logical operations that we need to do on the qubits within quantum computers have proven to be too high for most practical applications. This is no longer a question of how many qubits are in a processor or even what the coherence of these qubits is, but how the controls are introducing errors at every step of the computation with a fraction of a percent probability. And this really limits the complexity of the algorithms that can be implemented. Now, there is a way around this, and this is something that as an industry we've known for some time, but that, of course, it has taken a lot of effort to get us close to being able to deliver on. And this is the idea of logical qubits, in which using the tools that were initially developed for the classical computing and communication world, in which error correction allows to improve the effective error rates of systems by taking a single unit of information, in our case, a qubit or a logical qubit, and encoding it redundantly in a larger number of physical qubits. This way, as the computation takes place and errors are potentially introduced, it is possible to check whether an error in the computation happened and to be able to correct it without affecting the rest of the processor. This way, the error rate can be reduced in order to continue scaling the power of quantum computing to get to larger and, of course, much more meaningful quantum algorithms.
And error correction is difficult. It requires a lot of different things to be in place. And over the past few years, Alex QuEra's, under your leadership, has worked on building these together with our partners from Harvard and MIT and others. So perhaps you could talk about what are the key building blocks? What needs to be in place in order to implement effective error correction?
Absolutely. I'm going to focus on four things here. One is the physical platform, how we build qubits. The second one is how we think about the connectivity within the processor. The third one is how can we use resources efficiently to do computations in as much as possible in a parallel way. And the last one will be how everything comes together into an architecture. So let's jump straight into the first topic and how we actually make qubits. In our case, the technology that we have at QuEra's and that we have been developing as a community for a long time, this is all based on utilizing atoms, the fundamental unit of matter, to turn it into the fundamental unit of computation in the qubit. Atoms are identical. Every atom of a kind is identical to every other one. And this makes it possible to tune parameters and understand how to very finely control a single qubit, and then to scale that up to control many qubits simultaneously with the same controls. Atoms are very clean quantum objects. We understand them, and we can isolate them from the environment to preserve coherence and keep their quantum properties over long periods of time. All of this is done at room temperature without cryogenic systems required. And this simplifies the ability to scale up the number of qubits that we have in our processors. Now, the biggest threshold so far in terms of compute fidelity has been given by the ability to perform high fidelity operations between pairs of qubits in what we know as entangling gates. And above a threshold of 99% fidelity, it is possible to start thinking and implementing quantum error correction. This threshold was just crossed this past year for the neutral atom platform in work performed primarily at Harvard that QuEra has been supporting. And now it's something that we're very excited to bring into our own devices, where the fidelity of these entangling operations at scale with multiple pairs of qubits simultaneously has been brought up to 99.5%. So this is the physical platform. It gives us already an excellent starting point to build scalable systems with many, many qubits. And the next thing is, how do we make sure that we're using these qubits to their fullest possibilities by connecting different parts of the processor together? Having a limited local connectivity can be a challenge, but thanks to the way in which our processors are built, and here represented by this video of the first implementation of the idea of qubit shuttling that was demonstrated at Harvard in 2021, what is possible to do now is to take qubits and move them around within the processors throughout the computation to ensure that any pair of qubits can be connected in a single step operation. This reduces the number of controls that are necessary to put into the system, and it allows us to do complex algorithms using the neutral atom platform in using only very few classical controls. Now, this enables the next step, which is how do we perform operations between logical qubits? And logical qubits are built, as I mentioned, by connecting different physical qubits into a single block that redundantly encodes information. Now, by being able to move these blocks and connect them directly, we can enable what are known as transversal gates. For certain quantum error correction codes, it is possible to apply the same operation to all physical qubits in a single logical qubit and perform the logical operation that is desired. This makes the process of implementing logic gates on logical qubits much more efficient. And thanks to the ability to move qubits and connect them directly, we can now start thinking about quantum error correction codes, such as the surface code that is one of the most studied codes in the industry, to implement also entangling gates between logical qubits in a fault-tolerant way, simultaneously in a single step. This reduces significantly the number of physical operations that are necessary to do between logical qubits to create that necessary entanglement between them. And these ideas come together in an architectural view that was first demonstrated just at the end of last year on research led by Harvard University, where the processor can now be segmented into different functional zones, very much like how we think about classical compute architecture. Particularly, this iteration of the architecture has a storage zone where blocks of logical qubits can all be stored and maintain their quantum properties. And the whole block can be moved all at once into an entangling zone where we can bring pairs of logical qubits together now in a single move operation, and using a single control that is calibrated only once, perform these entangling operations between logical qubits in this entangling zone. Last but not least, we can then take this architectural view to also add a readout zone that allows for the fast recovery of information in a way that doesn't disturb the rest of the qubits. This way we can extract enough information to be able to feed back on the system and implement quantum error correction while preserving the coherent information in the logical qubits. This architectural perspective was used in a publication that came out at the end of last year, led by the Harvard team with support from QuEra, both providing technical expertise, equipment, and also having QuEra personnel participate in the publication. But again, this was so far demonstrated on the device that was built and operated at Harvard by the Harvard team. Now, the key breakthrough here was to use this architectural approach to implement complex algorithms already with up to 48 logical qubits. And I want to show you what the dance of the qubits looks like, so that you can get an idea of how being able to move atoms and have logical operations happen in a single step looks like. Here, the storage zone at the top enables to store multiple logical qubits simultaneously, and in the entanglement zone, by bringing atoms together and performing entangling operations between physical qubits across the different blocks, enables this complex algorithm to be implemented with 48 logical qubits. This is by far the largest demonstration with logical qubits, and it speaks to both the ability to have and control multiple, hundreds of physical qubits, but also how to use the control, the classical controls efficiently. Just for a sense of scale, this demonstration with 48 logical qubits consisted of a total of 228 logical entangling gates. This algorithm consisted of 228 logical entangling gates between pairs of logical qubits, as well as 48 entangling gates between 3 logical qubits at once, which, as you'll hear a little bit later, is an important step towards expanding the use cases that are available with quantum computers. Now, other highlights from these results include the preparation of different error correction code, surface code, and seeing the expected scaling behavior by increasing the distance or the overhead in the quantum error correction code, reducing the error in entangling gates between pairs of logical qubits, going from a distance 3 to a distance 5 to a distance 7 error correction code. Using yet another type of quantum error correction code, color code, with 7 physical qubits per logical qubit, it was demonstrated that logical operations can have break-even fidelities relative to the physical counterparts, and using them, it is also possible. Using these logical codes, it's also possible to create fragile quantum states known as GHC states that hold that are very sensitive to the environment, showing the high performance of the system, as well as using mid-circuit measurement and feed-forward tools to take operations between logical qubits and translate them to different distant qubits. Now, all of this is, of course, something that we are extremely excited about, but to this day, it has been demonstrated only once in a university setting.
And this is a very interesting point, and I wanted to just add some color on the zoned architecture. When you think about your desktop computer, a classical computer such as the one you're using to experience this webinar, it has a processor and it has memory. And basically, the computation is done by the data being moved from memory to the registers in the processor, some operation happens, and then data is moved back. And one of the fascinating things about that is that you can double or triple the memory without changing the processor. The analogy in the quantum architecture that Alex presented is exactly the same. You could have a fairly large memory and then move the data, move the logical qubits or move the qubits into the entanglement zone, perform operations on them and take them back. This is also very useful for scaling. One of the things that people worry about is, okay, you can do this with 10 qubits or 100 qubits or 1,000 qubits, but how do we get to tens of thousands or millions of qubits without having tens or thousands or millions of controls? Think about the classical analogy. If you were to open your 4K television and discover that the wire was going to every single pixel, that would be a problem. That'd be a very heavy and expensive television. And the zoned architecture that we described is very efficient in that. In fact, in the Harvard, QuEra, MIT experiment, we controlled 300 qubits with about 10 controls. So the number of controls does not scale linearly with the number of qubits, more of, you can think about it logarithmically. And that's one other reason that we're very confident that we can scale to a very large number of qubits in a realistic manner. But as you said, Alex, this is fantastic theoretical and experimental research. I think Scott Arneson called it perhaps the most exciting experimental result of 2023. But how do we get this to the market, and what kind of experience does QuEra have in taking innovations quickly to the market?
Yeah, I think you said it at the beginning of this presentation, right? You know, what we do at QuEra, what we have done over the last several years, is to take the most advanced breakthroughs in science and convert them into products that we can take to customers. Particularly when you look at the history of QuEra and where we come from, the work that we're doing really started earlier than the foundation of QuEra by research that was primarily performed at Harvard and MIT that led to the demonstration of programmable quantum processor with 51 qubits in 2017. This, of course, was a very important advance in the field. And thanks to that and a few other key breakthroughs that came through the intervening 2 years, QuEra was founded in 2019 to take these results and translate them into product and bring them to customers. The first example, we talked about Aquila early in this webinar. And Aquila is an excellent example. When you look at when the first demonstration with 256 atomic qubits was done, this was led by the Harvard research, and the results were presented in July of 2021. At QuEra, we worked tirelessly to take these advances and turn them into a system that we connected to the cloud and made available to all customers everywhere around the world in just a little over a year after that. So this, to my knowledge, is the fastest lab-to-market transition for quantum technology, and it is a processor with up to 256 qubits that anyone around the world can access thanks to our partnership with Amazon Bracket. Now, this all has been happening in what we call the era of physical qubits, but given the results that have come out in the last year, I think that the last year has been instrumental to the quantum computing industry. We are taking the work that has been done to increase the fidelity and operations to build this new architecture and to take us into a new era of logical qubits, into also products that we are now building that we will make available to customers very soon. So again, this is a transition moment for our entire industry where we are going to be bringing the newest capabilities to start a new era of logical qubits. And the first step towards this, and in preparation of it, is that we are announcing today that we will make available to customers later this year our first logical qubit simulator. This will give users access to tools like visualizer to understand how a quantum algorithm is broken down into the basic instructions for this architecture with moving atomic qubits, and to be able to tune the parameters of their algorithms and understand what the time and requirements are, and how to use different representations of particular algorithms to make them more efficient for the hardware. This way, we expect that users will generate their own IP, and particularly by adding lower level intermediate representation access, we expect to see a lot of middleware solutions come to bear that will be building on top of the platform that we will make available to customers. As time goes on, we will continue to update realistic noise models so that users can understand how far they can take any one generation of our technology, and to also start playing around with the different forms of quantum error correction codes that they can use. So again, this is something that we're very excited about, to bring the community together to develop their algorithms for this new neutral atom platform, and it will be available to select customers and partners later this year. Now
we've seen that mode of operation even with our current system with Aquila. We have an open source software called Blockade that allows people to test algorithms, simulate them on their desktop computers before submitting to the machine, and then that both saves the machine time and allows them to experiment with different configurations. Of course, they cannot simulate 256 qubits on a classical machine, but they can run a small-scale algorithm. But as much as we like software, we love hardware, right? So maybe we get to the highlight of the presentation, and Alex, could you lift the veil and tell the audience what computers we have coming in the next couple of years?
Of course, and let's start by a very brief recap. You've heard a lot about Aquila. Aquila provides 256 physical qubits, and there's a reason why I'm pointing out the number of physical qubits. It has been used for applications in quantum simulation, optimization, and machine learning. This has all been done in the context of an analog computing platform. As you heard, we'll continue to support that, but our second generation that we'll make available later this year, this is hardware that will give users access to over 256 qubits with all the tools that you heard about, in order to be able to build up to 10 logical qubits and start implementing algorithms on them, understand the performance, compare it with the logical qubit simulator that will be available, and particularly using the transversal gates that I described, we expect to see a very hardware efficient utilization of these logical qubits. Moving into the year after that, in 2025, our third generation devices will give users access to over 1,000 physical qubits to build up to 30 logical qubits. And one of the things that we mentioned very briefly is the ability to implement gates that are known as non-Clifford gates. This was in the recent results in the context of the control phase gate, but these non-Clifford gates are yet a new tool to be able to add in a hardware efficient way that will give users access to much more complex and meaningful quantum algorithms that they'll be able to now implement with up to 30 logical qubits. We want to see customers grow their applications together with the hardware capabilities and go from these 10 to 30, and of course, leading into the fourth generation, 2026, 100 logical qubits. This, I think, is a very important moment. 100 logical qubits with effective error rates that are low enough so that the whole processor can be used very effectively in a non-reducible way. So what are we talking about here? We're talking about being able to run any abstract algorithm and knowing that the algorithm is running properly without introducing errors, already at a scale that is no longer simulatable using classical resources. At 100 logical qubits, we expect users to enter a new era of discovery in quantum algorithm development. Here, I believe, and I don't know about you, Yuval, but I am much more interested about how many logical qubits we have and how many physical qubits there are. And this is the approach that we say that our customers will have as well. This is really the point at which they can find applications that would be impossible to predict ahead of time, and where they will be able to take the algorithms that they have been developing for the 10, 30 logical qubit devices into the unknown.
Absolutely. And, between us, we're just the two of us right now. Quantum computers today are almost useless. I mean, they're, of course, very useful as you want to prepare for larger and stronger and more powerful quantum computers. But with a few exceptions, anything that you can do on a quantum computer, you can do classically today. But this fourth generation, 100 logical qubits, dramatically changes that. At this time, you will have results that are correct, that we know that are not error-prone, but that you could not simulate, you could not calculate on even the world's fastest supercomputer. So you're absolutely right. This is what gets us excited. This is one of the reasons that we get up every day and strive to get this kind of amazing technology as fast as we can into the market.
That's right. And, this is the view for our next 3 years. This is our quantum roadmap to error-corrected devices to get us to that next and biggest inflection point in the industry. But for right now, for today, what can you tell us about how users can engage with QuEra?
Absolutely, because we're doing this for you. So there are several ways in which you can engage with QuEra. The first thing is we've opened an access waitlist. So there's a form on the website. You can see the link and the QR code on the top right. And this is an opportunity for you to say, what do you want to use and what will you do with logical qubits? And then we'll work with as many of these customers as we can and provide them early access both to the simulator as well as the hardware. So if you're an end customer and you want to explore quantum error corrections applications, or if you are a national program or an HPC center that wants to purchase one of these computers, absolutely, we want to hear from you. There's a contact us link and QR code in the middle of the slide. If you are a middleware or researcher that wants to optimize the software stack because there's work to be done on qubit shuttling, on trajectories, on QEC codes, and so on, we'd love to hear from you because we're building a amazing ecosystem around this world-leading hardware. And if you're looking for your next technical adventure in Boston, we're hiring for multiple positions. So please visit our website to see that. We have, during this webinar, we've seen many questions come on the Q&A. We've tried to answer as many of them live as we can, but we'll get to them later today or tomorrow. You'll also receive an email that allows you to, we've created a special quantum error corrector that we'd love to share with you, and maybe some other goodies if you're interested at no cost. And Alex, if you can move to the next slide, please. We'd love to speak with you, and we'd love to walk with you and welcome you to the era of logical qubits. Alex, thank you very much for spending some time with us, and thanks all the audience members. We're very excited about this direction, and I hope you are as well.
Thank you. And thanks, everyone.